All right, today we are diving into the absolute core of what makes models like GPT tick. It's a mechanism called scale-product attention. Sounds a little technical, I know, but trust me, this is the secret sauce. This is how AI really understands context, and we're going to break it all down. Let's get into it. Okay, so here it is. This is the formula that basically turned the entire field of AI on its head. And yeah, I get it. It looks intimidating, right? Whole mess of letters and symbols, but I promise you, by the end of this whole equation is not only going to make sense, it's going to seem elegant. So let's think of this as a bit of a mission. We're not just sitting through a lecture. We are on a quest to crack the secret code that powers modern AI, and we are absolutely going to crack it together, step by step. But first things first, to really appreciate why this formula is so darn brilliant, we have to understand the problem it was built to solve. We've got to start by looking at an older, much simpler method that, well, just couldn't get the job done.
So the original idea seemed logical enough. Every word can be turned into a list of numbers, a vector that kind of captures its meaning, its vibe. And if you want to see how related two words are, you just calculate their dot product. The higher the score, the more related they are. Simple, right? Well, the real world is a bit messier than that.
Let's take a look at this sentence. When you read the word it, your brain instantly, without any effort, knows that it refers to the ball. But how on earth is a machine supposed to figure that out? This is exactly where that simple old approach starts to break down.
Now, here's where it gets really interesting. Look what happens when we use that simple dot product. If we run the numbers for dog and it, and then for ball and it, we get the exact same score. So what does that mean? It means the model is completely and utterly confused. It has no mathematical way of knowing whether it refers to the dog or the ball. It's a 50-50 guess. And that kind of ambiguity is a massive, deal-breaking problem. The simple method just doesn't work. So, how do we fix this? Well, the genius idea wasn't to throw away the dot product entirely, but to make the inputs way smarter. Instead of using those raw word vectors, we first transform them into three specialized versions: a query, a key, and a value. Here's the basic idea of how that works. You take an original input vector, let's say for the word ball. You then multiply it by a special grid of numbers, a weight matrix, which we'll call WQ. Now the magic is that this matrix is trainable. The model actually learns the perfect values to put in there during training. And the result? You get a brand new vector, a specialized one, called the query.
And this doesn't just happen once. For every single word in the sentence, we do this 3 separate times with 3 different trainable matrices. So now each word gets a query vector to kind of ask questions, a key vector that acts like an identifier, and a value vector that holds its rich, meaningful information.
And would you look at the power of that transformation? Check out these new scores. The dot product between the transformed dog and it is now way lower than the score between the transformed ball and it. The confusion? It's gone. The model now knows exactly what it is referring to. Problem solved. Okay, so now that we get the why behind all this, we are finally ready to go back and face that formula. It's time to decode this thing one piece at a time.
The first part of the formula, Q times K transpose, is basically our new and improved dot product. You can think of this as the matchmaker. It takes the query vector, the question, and compares it against all the key vectors in the sentence to find out who's a good match. This process gives us our raw attention scores.
Next up, we divide everything by the square root of d sub k. Think of this as a stabilizer, or maybe like a volume knob. As the vectors get longer, those dot product scores can sometimes get really huge, which can make the model unstable when it's training. So this little division just keeps all the numbers in a nice, healthy, manageable range. It's a small but crucial step. Then comes the softmax function. This is our distributor. It takes that list of stabilized scores, which can be a little messy, and it works some magic, converting them into a clean list of percentages that all add up perfectly to 100%. These are our final attention weights, and they tell the model precisely where to focus its attention. And here's what that looks like in action. For the word ball, you can see the model has learned to distribute its attention. It pays the most attention to itself and to the word chased, which, makes perfect sense. The ball was chased. It has actually learned the grammar and the context of the sentence. So, we have our attention weights. We know exactly where the model should be looking. But we're not quite done. There's one final step, putting it all together to create the actual output. And this is where that third vector, V for value, makes its grand entrance.
Remember the v-vectors? They're the ones holding all the rich, meaningful information for each word. Well, the attention weights we just calculated are basically the recipe. They tell us exactly how much of each word's value to blend into our final mixture.
So the process is what's called a weighted sum. It's pretty simple, really. You take each attention weight, that percentage, you multiply it by its corresponding value vector, and then you just add them all up. What you get at the end is a brand new vector for the word ball, but this one is now deeply aware of its surroundings. It's packed with context, which is exactly what we wanted all along.
And this chart really hammers home the power of this whole process. We started with these generic, isolated input vectors that didn't know anything about their neighbors. And now we end with a full set of new vectors where each and every one has absorbed relevant information from the entire sentence. They're now context-rich. So, okay, we've decoded the formula, we've cracked the code. But let's zoom out for a second. Why does this one equation matter so much? What's the really big picture here? At the end of the day, this whole mechanism is what gives AI the ability to weigh the importance of different words and truly understand how they all relate to each other, even across really long sentences or paragraphs. It's the magic that allows a model like GPT to generate text that feels so coherent and, well, so human. So, to recap the whole journey, we transform our basic inputs into specialized query, key, and value vectors. Then, we use them to calculate attention weights, which map out all the relationships in the sentence. And finally, we use those weights to build powerful new vectors that are fully aware of their context. That, right there, is the beating heart of pretty much all modern language models. You know, this formula, as complex as it first seemed, is an incredibly elegant solution that truly changed the entire course of artificial intelligence. It really makes you wonder, doesn't it? What other secret codes are being worked on in a lab somewhere right now that are going to unlock the next great leap forward?